So let's go ahead and try this problem. We've got a ball, it's right there, it's rolling along this track that we've got, and if it starts from rest here, they want us to tell them how fast is it going here at B and how fast is it going here at C. They also say that there's no drag and friction that we've got to pay attention to, they're just too small to make a difference here. So we could certainly do this, if we really knew the details of the track using forces and accelerations, but it'd be a real pain because of course like the component of gravity that is sort of along the track is changing. The angle here is different from the angle there, is different from the angle track. It's a big old mess. So probably what we want to do is use the work and energy model. So this is the equation that we always use, those non-conservative forces that do work. They are equal to the change in the kinetic energy plus the change in the potential energy. And first we got to figure out, do we have any forces that aren't conservative that are doing work? So what forces do we have here? Well, certainly gravity. That is going to be affecting it as it moves along. We don't have friction, we don't have drag, there's no springs, there's no strings, so no spring force or tension force, but there is a surface. So there's also the normal force. So gravity, that is a conservative force, it has a potential energy. We are going to feed it into the model over here in the potential energy. The normal force, does the normal force do work? Well, let's take a look. At every point along this track, it's going to be traveling along the surface of the track like that. So that'll be the direction of its V. But the normal force will be normal to the surface, which is going to be perpendicular to how this thing is traveling. So the normal force does no work. The work done by the normal force is zero because it's always perpendicular to the direction of motion, perpendicular to the displacement. So we don't have any non-conservative forces doing work. So this guy is equal to zero. Great, so the mechanical energy is conserved. So let's figure out point B. At B, we know that there are no non-conservative forces doing work. So this side of the equation is zero. And we've got the change in kinetic energy. So the change in kinetic energy is 1/2 the mass times the final speed squared. I guess that here is going to be the speed at B minus the initial speed, which is going to be the speed at A. And then potential energy, we don't have a spring, so we've only got gravity. So that'll be mass times G times the height at the end, the final height, that would be the height at B, minus the height at the start, that would be the height at H. And we know those heights, so that's good. We know the mass, we know G, so all we've got left are the speeds, which are the things we're interested in. And we know it starts from rest at point A, so that tells us that this guy is equal to zero. So let's go ahead and solve for VB. So that one's zero. Let's go ahead and move this term over to the other side. It'll pick up a negative sign. So minus 1/2 the speed at VB squared equals mg, difference in those heights. And we'll divide by negative 1/2 m to isolate VB. Those guys will cancel out on this side. Oh, and a mass will cancel it over here. That's very nice. So VB squared is equal to, well, we're dividing by 1/2. That's the same as multiplying by 2. And we got this negative there. So 2g, change in height. All right, let's go ahead and plug in the numbers. And I guess we'll take a square root while we're at it. And hopefully something will take care of that negative sign. Don't want to take square roots of negatives. Get imaginary numbers running around, that's no good. All right, so 2 times 9.8 meters per second squared. And I do want to say this G always, always, always going to be plugged in as the magnitude as positive 9.8 meters per second squared in gravity, because here the negative sign is telling us about sort of time. Final position, initial position. So you don't want a negative sign to be added in with the G, because for work and energy, negatives mean a totally different thing than they do when we're dealing with vectors, which is the force and acceleration. So just, again, emphasizing this should be the positive 9.8 meters per second squared. Okay, end of rant. Height at B, that's 15. Minus the height at A, that's 25 meters. Square root of this whole thing. VB, all right, negative 2 times 9.8, that is negative 19.6 meters per second squared. That times 15 minus 25, that's negative 10 meters. Oh, good, so we get a negative times a negative, they'll be positive. So VB is going to be the square root of positive 196 meters squared over seconds squared. Go get the calculator to do that square root. That will be 14, and the meters squared over the seconds squared, when you take square root, that'll be meters over seconds. So at VB, speed is going to be 14 meters per second. Great, let's do the same thing for C. And same stuff's going to apply. We don't have any non-conservative forces doing work, because the only other force than gravity is the normal force, and it doesn't do any work because it's perpendicular. And gravity is not a work anymore, it's potential energy. So now, instead of doing B as our final position, we're going to do C. So everything will be actually exactly the same. So we'll still have 0 for the non-conservative forces doing work, no net work done by them. 1/2 the mass times the final speed, that is now the speed at C, that's our endpoint now, minus our initial speed. That's the speed at A, but we already said, oh, it starts from rest, so that guy's 0. Plus the change in potential energy, and our final height is now the height at C, minus our initial height, that height at A. And you can see these are very similar equations, so all the algebra will be exactly the same, and we will get to this point. The velocity, or the speed, sorry, at C equals the square root of negative 2g. Instead of ending at H, sorry, at any HB, we're now ending at HC. That's the only thing that's changed in between these two equations. This guy and that guy, where we're ending up. So this will be HC minus HA. Take the square root here, and then we'll plug in those numbers. Negative 2 times 9.8 meters per second squared. HC, that's 10 meters. HA, that's 25 meters. And this will be square root of negative 19.6 meters per second squared. This will be negative 15 meters. Again, we got those negative signs canceling out. Always good when you're under the square root and not expecting an imaginary number result. And together, those are going to be the square root of 294 meters squared per second squared. And when we take the square root of that, we get 17 point stuff. We'll just keep 2 sig figs. Meters squared will be meters over second squared. Take the square root, that's seconds. So here, at point C, the velocity is 17 meters per second. So, much less algebra than we'd normally get in a force problem like this. But we get our answer, and let's go a little bit deeper here. So we are banking on the fact that we have no non-conservative forces moving energy into and out of our system. So this is an isolated system, this little ball here traveling along. No non-conservative forces doing work on it. So its mechanical energy is conserved. So we go ahead and plug in 0 for the exchange of energy with the outside world from the non-conservative forces. Look at the change in the kinetic energy. Look at the change in the potential energy. Algebra, algebra everywhere. algebra, algebra everywhere, and get to our answer. But now let's go ahead and look at what's going on with the energy at all the points A, B, and C here. All right, so looking at the energy, and in particular the mechanical energy here. Point A. You can look at its kinetic energy and its potential energy due to gravity. The kinetic energy is 1/2 mass v squared. Potential energy due to gravity is mgh at A minus a constant. So I guess we need to figure out where do we want the potential energy equal to 0, so we can figure out what that constant is. Okay, so looking at this, I say let's go ahead and make it actually at this lowest height here. That'll be our reference point for the gravitational potential energy. Okay. So right there, our potential energy due to gravity is equal to 0. That's going to be our reference point, and that's the same as saying our height is equal to 0 right there. Okay, so if we know that, that means we want to measure these heights relative to this one. So to figure out our potential energy here, what we'd want to do is do our height relative to this guy. So it's actually going to be this height minus that height. So minus the height at C, because that's our reference point. That's where we're setting the potential equal to 0. All right, so if we do that, well, the kinetic energy is easy to solve for. It's at rest here, so that it has no kinetic energy, no energy due to motion. The potential energy is 1 kilogram times 9.8 meters per second squared. Again, remember, we're just plugging in the magnitude. No negative signs here in G. Difference in height is 15 minus 10, 25 minus 10, which is 15. Doing the math already in my head. So this height minus that height, because we picked this to be our reference point for potential energy. And if we plug that in, 1 kilogram times 9.8 meters per second squared times 25 minus 10, get our calculator. This is going to give us a potential energy of 147 joules. Okay. So on A, we have a kinetic energy of 0 and a potential energy of 147 joules. So our total energy is those two added, 147 joules. Again, remember that's kinetic plus potential. Let's look at point B. So our kinetic energy here is 1/2 the mass times the velocity. We've got it b squared, and we actually knew that it's going to be the square of this, so 196 meters per second squared. The mass is 1, so 1/2 1 kilogram times 196 meters squared per second squared. And again, I got that here just by squaring that number or by simply failing to take the square root. And when I go ahead and plug that in, do the math, I get 98 joules. And if I do the potential energy, that is mass times the difference in height. Again, remember I'm using this as my reference point, so height B minus height C. If we run that through the mass, we get 1 kilogram times 9.8 meters per second squared times height B, that is 15 meters, minus height A, that's 10 meters. And when we do this, we are going to get 49 joules. So that is our potential energy at B. Here's our kinetic energy. And the total energy, when we add that kinetic plus that potential, here it is at A, here it is at B, they will add up to 147 joules. Again, of course they should, because mechanical energy is conserved. And then point C. Kinetic energy here at C is 1/2 mvc squared. So that is going to be 1/2 times 1 kilogram for the mass times 294 meters squared per second squared. And that is going to give us 147 joules. And the potential energy at C, well, that is the mass times gravity times our height at C minus our reference height. Oh, that's C. And this, of course, is going to be 0 because that is where we set the potential energy equal to 0. So the total energy here, the kinetic energy at C plus the potential energy at C, those guys are also equal to 147 joules. So we got the same energy everywhere, and we're just passing it back and forth between kinetic and potential. So here at point A, it's all potential, no kinetic. Here at point B, it's no potential energy. All that energy is kinetic. And here at point B in the middle, some of it is kinetic, some of it's potential. So you're just sort of passing it back and forth between energy types. So that's how you would do a work energy problem here using conservation of energy.